Look up at the night sky, and it feels empty, silent, endless. But above that silence, Earth is surrounded by thousands of machines, moving fast, invisible, precise. These are satellites, and every single one of them follows a path called an orbit. But here's what most people don't realize. There is not just one type of orbit. There are many, each one designed for a specific mission: communication, navigation, weather tracking, military surveillance, and deep space exploration. It all began in 1957 when the Soviet Union launched Sputnik 1, the first artificial satellite in human history. Since that moment, humanity has placed thousands of satellites into space, and each one follows the invisible rules of gravity and motion. In space, orbit is everything. It decides what a satellite can see, how fast it moves, and what role it plays in modern life on Earth. So let's explore the hidden structure above our planet and uncover the different types of satellite orbits.
To understand satellite orbits, we first need to understand space itself. An orbit is not just movement, it is a balance between two forces: gravity, pulling everything toward Earth, and speed, pushing the satellite forward. When these two forces are perfectly balanced, the satellite keeps falling but never hitting the ground. It continuously misses Earth, creating an orbit. This principle was explained through Isaac Newton's laws of motion and later refined through modern orbital mechanics. Without this balance, satellites would either crash into Earth or drift away into space. But with it, they become stable machines circling our planet. And depending on their height and purpose, their orbits change completely.
The closest satellites to Earth operate in low Earth orbit, or LEO. This region begins at around 160 kilometers above Earth and extends up to about 2,000 kilometers above the surface. Satellites here move extremely fast, completing an orbit in about 90 minutes. One of the most famous objects in LEO is the International Space Station, launched in 1998. It orbits Earth at around 420 kilometers above the surface. Then there is the modern Starlink satellite network, operated by SpaceX, with thousands of satellites providing global internet coverage. LEO is also used for Earth observation satellites, tracking climate change, monitoring disasters, and capturing high-resolution images of the planet. But there is a challenge. Because LEO is close to Earth, it is also crowded. Thousands of satellites and debris move through this region at extreme speeds, making collision avoidance a serious problem today.
Beyond low Earth orbit lies medium Earth orbit, or MEO. This region extends from about 2,000 kilometers to 35,786 kilometers above Earth. Satellites here move slower than LEO satellites, but cover much larger areas. The most important satellites in MEO are GPS satellites, first launched by the United States starting in 1978 under the Navstar program. These satellites orbit at around 20,200 kilometers above Earth. They form a global navigation system that allows smartphones, airplanes, and military systems to determine exact locations anywhere on the planet. Without MEO satellites, modern navigation would not exist. They are invisible but essential, guiding everything from maps to global transportation. At 35,786 kilometers above Earth lies one of the most important orbits ever created, Geostationary Orbit, or GEO. Here, satellites orbit at the exact same speed as Earth's rotation. That means they appear completely stationary from the ground. One satellite, one fixed point in the sky. This makes GEO perfect for communication satellites, television broadcasting, and weather monitoring. The first operational geostationary satellite was SYNCOM-3, launched by NASA in 1964. Today, weather satellites like NOAA's GOES series monitor storms like hurricanes in real time. GEO satellites cover nearly 1/3 of Earth each, making them essential for global communication networks. But signals take time to travel, creating a small delay known as latency.
Not all satellites stay over one region. Some travel from pole to pole. These are called polar orbits. In a polar orbit, a satellite passes over Earth's north and south poles on every revolution. Because Earth rotates underneath it, the satellite eventually scans the entire planet. This makes polar orbits ideal for mapping, environmental monitoring, and reconnaissance missions. Many Earth observation satellites use this orbit to capture global data over time. Each pass provides a new slice of Earth, building a complete picture of the planet's surface.
A special type of polar orbit is the Sun-Synchronous Orbit, or SSO. In this orbit, a satellite passes over the same location at the same local solar time. This ensures consistent lighting conditions in every image. It is extremely important for climate monitoring, agriculture, and disaster analysis. Satellites like Landsat 8, launched in 2013, operate in this orbit. Because lighting conditions remain constant, scientists can compare images over long periods with high accuracy. This makes SSO one of the most valuable orbits for Earth science.
Not all orbits are circular. Some are stretched into long ovals called highly elliptical orbits. In these orbits, satellites move close to Earth, then swing far into space and return again. One famous example is the MEO orbit, first used in the 1960s. This orbit allows satellites to spend most of their time over high-latitude regions, like Russia and northern Canada, where geostationary satellites are less effective. These orbits are ideal for communication in extreme northern areas.
Beyond Earth's immediate environment, there are even more complex orbits. Some satellites travel to Lagrange points, positions where gravity between Earth and the Sun balances out. The James Webb Space Telescope, launched in 2021, operates near the L2 Lagrange point, about 1.5 million kilometers from Earth. There are also transfer orbits used to move spacecraft between destinations, and graveyard orbits where old satellites are placed after retirement. Space is not just about staying in orbit, it is about moving through carefully designed paths across the solar system.
From low Earth orbit to deep space trajectories, every satellite follows a carefully designed path. These invisible highways above Earth power the modern world. GPS navigation, weather forecasting, global communication, internet systems, and scientific discovery all depend on them. Since 1957, satellites have transformed from experimental machines into the backbone of modern civilization. And yet, most of them remain unseen, silent, precise, and constantly moving above us. Orbit is not just a path in space. It is the structure that holds our connected world together. And as humanity continues to expand into space, new orbits will shape the future once again.